Steven Sims is a SANS fellow. He's been teaching SANS for quite some time. He's the author of multiple courses, including 660 and 760, which are the advanced pen testing and the exploit development courses, right? Which is pretty technical. Probably the most technical class I would say is 760. It's amazing. Shout out to those GXPNs. I see you there in Sim's chat channel. And overall, very, very nice guy. Curriculum lead of the offensive course. And I don't know what else to say about Sims. I feel like we can talk quite a bit of him, about his taste in music and beer, but we'll let Eric wrap it up and bring him on.
I'll just make it very simple. Steve Sims is the reason why, if you're taking 599, if your brain starts hurting on day 3, because we talk about exploit mitigations, it's his fault. It's not my fault. It's his fault. There you go. And with that, I'll just leave it to Steve to start talking. Enjoy, everyone. And yeah, looking forward to this one.
So thanks again for having me. I do appreciate it. And like Eric said, this material comes straight from 599, but it also comes from 760. So why in two such different courses? So in 599, we're taking more of a defensive take on this topic, and on 760 and a little bit in 660, which are the advanced exploit dev courses, we look at more of an offensive approach, or from an offensive perspective. So I thought, I don't get an opportunity often to teach this topic or to lecture about this topic, and I wanted to do more of a purple spin on it. So from an exploit development perspective, which is where I've spent a large portion of my career, how do these mitigations impact my ability to weaponize and actually exploit a vulnerability? Because a vulnerability, oftentimes, it's still there. It's the root cause of a problem, but the mitigations are what's preventing me from being able to actually exploit and take control of the affected system. So that's kind of the spin I want to take on this topic for the presentation here. So first, I want to talk about what are exploit mitigations, and a big shout out to especially folks like Matt Miller at Microsoft, who have done such amazing work over the years with implementing these controls. You may have heard of a mitigation toolkit called EMIT, the Enhanced Mitigation Experience Toolkit, it came out around the same time Windows 7 came out, and then after some time, it wasn't heavily adopted. I believe I remember seeing from Microsoft at one point, it was like a low adoption rate, around 5%. So they put a lot of time into this mitigation framework or toolkit, but not many organizations were actually using it in their environment. So when they decided to deprecate it or just stop supporting it, there was definitely some feedback from the community concerned around, well, we love these mitigations. How do we continue using them on Windows 10? And initially the response was, well, control flow guard, a particular control, was going to be kind of strong enough to satisfy a lot of the concerns or to solve a lot of the problems. And in fact, it's not quite there. It's a great control, but any one of these controls by themselves, you can typically get around. Not always, but a lot of times. It's like this Venn diagram you see on the slide here. It's when you're using many of these controls from different categories that life becomes very difficult from an attacker perspective. So we want to be there in the middle of the merged areas where we're protected by multiple mitigations at the same time, which is going to really raise the bar. So again, any one mitigation isn't always enough to stop an attacker. And so thankfully, Exploit Guard came out at some point in Windows 10. I think it was like 2019, October, somewhere around there. And it's been there ever since. But the problem is it's not on by default. And that's why I wanted to talk about this. Is really like my push, my pitch to say, from a defensive perspective, we should be using these controls because they really do hinder an attacker from being able to do what they want to do. On the slide here, this isn't anything official, but you've got operating system controls that are controls that must be supported and enforced by the operating system itself. Then you've got compile time controls. So a lot of the controls like control flow guard, for example, it's required to be supported by the OS, and it has to be compiled into every module. So there's a relationship there oftentimes. Other times it's a mitigation that purely is compiler supported, like for example, stack canaries. So stack canaries are something that you compile in and it's on by default unless you go in and turn it off. It's called the GS flag on the Windows side of the house. So let's just kind of move in. I don't want to spend too much time on just the summary. Now this slide here, someone, actually a couple people a long time ago bet me money that, but actually not money, they said they would buy me a beer every time I was able to utilize and sneak this slide into a presentation. So you may have seen it in a presentation I've given in the past, because I know that I'm going to get something by using it every time. And it actually does serve a purpose here, not just being funny, but you can see on the left, it says Windows without exploit guard. And there's that guy, I'm assuming it's a dog show person, and it says, look at my entire dog. Like the attack surface on that dog is massive, right? There's nothing protecting the dog. On the right, it says Windows with exploit guard, and clearly that is a heavily armored dog. So the attack surface, there's still a little bit of an attack surface, but it's much, much smaller. And that's kind of effectively what these mitigations are doing. And up in the top right, if you were curious, that's Windows 7. There's just really no way in protecting Windows 7 anymore, unless you're on the extended plan with Microsoft and you're paying for patches for the next year and a half, I guess you have left. But on Windows 7, the problem on those operating systems, and even a lot of them on Windows 8, is many of the mitigations that we're talking about aren't backported in. They weren't backported to other operating systems, so you can't be protected. And even that, like the ASLR, Address Space Layout Randomization implementation on Windows 7 versus 10 is going to be massive, the difference. For example, in the kernel, if you look at something like the randomization of drivers on Windows 7, 32-bit, or even 64-bit, the entropy is much, much smaller than what you have on Windows 10, 64-bit, which makes sense. So what are these mitigations targeting? Really all the different bug classes that are out there, and not just bug classes like use after free and type confusion, but also the techniques that attackers use, like heap spraying, for example. Well, there's heap spray protection that might help you. And other techniques attackers use, the mitigations are targeting both bug classes and techniques used by attackers. And that's really the focus there. So this, I got this from Matt Miller a couple of years back, but it's the last update I was able to get. And I've got a couple of these over the years. And again, it comes from Microsoft, and it's just a really neat kind of timeline look at the bug classes or the root causes of these vulnerabilities that are disclosed to Microsoft or discovered in the wild. And you can see, I'm not going to go through each category, but you can see where one bug class goes down, another one kind of picks up. And it makes sense when we find low-hanging fruit in one area, we tend to focus on that, and we start to mitigate that particular bug class or the vulnerability type. And then the attackers, of course, are going to move on to the next area where they can get some results. And then we focus our attention there. So it's kind of neat to watch the trends over the years. And then sometimes things resurface again as attackers find new ways to exploit something. Now this, again, a lot of these slides come from, as I described, 599 and 760. And this, I just wanted to do kind of set expectation, quick kind of example of a very simple, basic bug class that everyone knows about. And the joke there, example from 1947. The sad thing is, I remember reading Smash in a Stack for Fun and Profit from Aleph 1. And I remember people like Solar Designer and others early on saying that the day of write what where attacks or primitives and the day of stack smashing and overflows is going to be over soon. And I do agree that the golden age of hacking certainly was in the mid 90s to the mid 2000s. That was just a really great time. There weren't any mitigations or many firewalls or anything. And if you knew how to do some very basic exploitation techniques or use them, you would win. It was so simple back then compared to today. You really have to ramp up. And the sad thing where I was going is that this stuff is still possible. It's just like right now, Intel with the Tiger Lake CPUs, which is a relatively new one, which most people don't have. And the latest build of Microsoft Windows 10, like 20H2 and such, they support some newer mitigations that are supposed to finally stop buffer overflows on the stack with the use of shadow stacks and control flow enforcement technology. But the fact that we we can still do this today though, and that we need to rely on mitigations to protect us is kind of crazy. And yes, compilers are getting really good at saying, hey, this is a banned function. Why are you still using strcpy or basic memcopy? Those are functions where we get ourselves into trouble. I joke because a lot of people assume, well, don't use strcpy, use strncopy, or memcopy at least takes in a size or a length. But the problem is memcopy, if you ever used AFL, the American Fuzzy Fuzzer, or other fuzzers, or just looked at vulnerabilities over the years, memcopy is always there. It's like this function that shows up at the wrong place at the wrong time over and over again. And honestly, it's not memcopy's fault typically. Like if you take the DNS vulnerability, SIG-RED from last summer in 2020, it was memcopy was involved. It's like always there at the wrong place at the wrong time, because the way that the size, the length was being calculated ends up being bad based on a prior integer overflow issue, but memcopy is always there. So it's these deprecated functions shouldn't be used anymore, but Microsoft especially has this problem where they've got to support things for legacy purposes, and supporting things for at what point do you cut it off? And you're going to get people mad at you regardless. They're going to be mad at you if people can still exploit based on these deprecated functions or antiquated functions, but then they'll be mad at you if you stop supporting them because then their applications don't work. So it's kind of a catch-22. So in this example, very basic example, we've got a buffer overflow scenario. We've got a character buffer of 16 bytes. So we allocate that memory on the stack so it's able to hold 16 bytes. We need a function to then copy data into that buffer on the stack in this example. So down at the bottom, you see that an attacker or a user is running the program and they're sending in as argv1 12 A's. Okay, 12 A's, the buffer is 16 bytes. Strcpy takes in the input, copies it into the buffer. It doesn't take in a length argument. But as long as you don't put too much data in, you won't see any problems manifest or appear. So we're okay. But then the attacker goes and sends in 32 A's. And clearly on the right, you can see we've overwritten important stuff on the stack, notably the return pointer. The return pointer, I'm sure you're all aware, is how we get back to the caller. So whoever called this function involved in the overflow wants control back at some point. So when we go to pass control back, it's been overwritten with A's. So we get the ASCII to hex value 41414141, which is an unmapped memory and virtual memory, and that's why we get the crash, the segmentation fault. So the only reason I wanted to walk through this is to get you thinking while we go through these mitigations, how could we have stopped this from occurring? Like the root cause is the use of strcpy here. How can we protect it if that root cause can't be removed, if we can't go and fix the code? What's there to protect us? So that's what we're going to talk about, Exploit Guard. So this is supported on Windows 10 only. It's not backported. How does it work? Not all of the mitigations work this way, but many of them will basically do hooking, where when you go to call something like a critical function, and a critical function could be something that crosses trust boundaries or something that allows you to allocate memory or change permissions in memory or write into memory. Those types of things are alarming, they're concerning. So if we hook those critical functions, we can do some inspection. We can say, okay, I see that you want to allocate some new memory. Let me inspect the environment to make sure things look the way that they should look before I allow this to continue. So this is user land we're talking about. This is before we get into the kernel. We're inspecting things. And then if everything looks good, we pass control into the kernel, we continue. If it doesn't look good, we're going to throw an exception. We're going to probably terminate the process. So that's kind of the gist of a lot of the controls, is to inspect the environment during a critical function call to make sure that things look good, look safe. What things are they doing? That's what we're going to talk about. So it's important from an operational perspective to understand what kind of overhead these mitigations are going to have. Because obviously, if you start turning on all these mitigation, that's extra code that needs to run. So it's going to slow things down a little bit. And historically in user land where our applications run, if we slow things down a little bit for Chrome, that's not that big of a deal. But if we implement mitigations in the kernel, then it affects the entire operating system. So you'll notice if you look historically that there were fewer mitigations implemented in the kernel than there were in user land. And there's multiple reasons. One is overhead. One is the fact that if a mitigation causes a problem, and they certainly can, in the kernel, that's probably going to blue screen the box, and user land is just going to crash the application. And there's other reasons as well. Maybe if attackers are mostly focusing on user land vulnerabilities, that's where we're going to spend our time. And then if they move into the kernel, we're going to focus our time there. So there's a lot of reasons as to why. But the point here is you've got to test your applications to make sure that they are not negatively impacted by a mitigation being turned on. And thankfully, with a lot of these controls in Exploit Guard and even in Emmet, you can turn on audit mode. So you're not actually, it's almost like IDS versus PS. So if we want to look at this from a purple team perspective, so what do I mean by that? What does red need to know and what does blue need to know? I care about how much do these impact my ability to be able to weaponize a vulnerability and get code execution or get an information disclosure bug working. That's what I care about. So from a defensive perspective, like offensive, I need to know how to get around it. And if I can get around it, defensive, I want to know, well, I've got to consider if I turn on every single control, because none of these controls are turned on by default. You have to go in and turn them on. And sysadmins are going to be maybe a little bit concerned about turning these on because maybe they don't understand what they do and they're afraid that they're going to negatively impact their production environment and cause things to break. That's, a resume generating move potentially. So there could be some just misunderstandings there. And so if it's off, I'm not going to go spend the time to turn it on. So I want to talk about which ones are going to make the life of an attacker more difficult since we maybe can't turn all of them on. So export address table filtering. This is really a mitigation targeting shellcode execution. So shellcode oftentimes wants to, like Meterpreter, for example, in order to be able to do what we need to do on the target system that we've exploited, shellcode needs to be able to locate things. It needs to be able to find kernel 32. It needs to be able to walk the export address table to look at the exported functionality to be able to locate function calls. It needs to know what the addresses are of things like load library and get process address and such. So this mitigation focuses on that. It says, let's not let the export address table of certain critical libraries be walked. And we can even add additional ones as well, or who should be able to access the export address table of these things. So it's pretty good at hindering shellcode execution. Import address filtering. This is, instead of the export address table that are used by libraries to export functionality, the import address table is what we use for dynamic dependencies. So if I am an application, I have dependencies on libraries that I expect your system to provide. So we load those libraries into the process space, and then we resolve the addressing and write that into the imports section. So what this does is it says, if an attacker knows that function calls are made from the import address table, right? We need to link this functionality. If they can overwrite an entry in the import section, when the process goes to call that function, if it's been overwritten by an attacker, we're gonna call the attacker's code. So if I can overwrite an entry in the import section and that function gets called, my attacker code gets called. That's what I want as an attacker. From the defender or defensive perspective, what this does is it says, validate that the address to be called during this function call resides within the associated library where it should. So if an attacker has dynamic memory allocation and they've got their shellcode sitting out there and we go to call that function, it's going to say, wait, the address we're about to call is not associated with the loaded library. Terminate. So that one's a pretty effective control if the attacker's goal is to hook an entry in the import section. Mandatory ASLR. So this control is, we've all heard of Address Space Layout Randomization. As humans, we like to know where things are. If things get moved all the time, that can be frustrating because we have to go and look for it. From a defensive perspective, if I don't want you to find something, I'm going to keep moving it. And the more space where we can hide things or move things, the harder it is for an attacker to guess or know where something is. So as an attacker, we rely on information disclosure bugs or static modules. This mitigation does not protect against information disclosure bugs. So if I can get a memory leak and leak out the address of something, I can calculate the offset relatively and get the base address, and it's game over. This doesn't protect against that. This protects against attackers who rely on modules that were not compiled to participate in ASLR. It's the dynamic base flag at compile time. This is not typically a problem with Microsoft DLLs. This is a problem with third-party applications where they weren't compiled to be randomized. For the most part, applications won't be negatively impacted if we turn this mitigation on. And it takes away low-hanging fruit. By low-hanging fruit, I mean, if I as an attacker can find libraries that are not randomized, it's game over. We can generate a ROP chain really easily and turn off the permissions that are negatively impacting my exploit, and it's easy. So this one is more of like, yeah, turn it on. It really doesn't add much overhead, and it does get rid of some of the low-hanging fruit, but it doesn't stop information disclosure bugs. Bottom-up ASLR. This is, I consider this one to kind of work alongside of mandatory ASLR. So remember, ASLR on Windows 10, it's on by default. The stack, the heap, it's randomized, but libraries may not be. So mandatory ASLR says, yes, you are going to be randomized, even if you were compiled not to be. Could it break something? Small chance, just test it. So bottom-up ASLR works hand in hand with that. And it says, so a problem on Windows is when you reboot the Windows OS, the libraries are randomized once per boot, and they stay at those same, they'll be loaded to that same addressing for the duration of that, the uptime on that OS. If you reboot it, it re-randomizes. And so if an attacker can figure out where one library has been loaded, they're usually loaded in succession. Even when the OS is rebooted, you can find where the other libraries are pretty easily if you can locate one. And what BASLR does is it says, before we load a library, choose a random number between 2 to the 8th power, and then block out a number of 64K allocations based on that number that was randomly selected, and then load the library at that offset. So it's going to take away some of the predictability that an attacker might have as to where a library is loaded. So it's okay. It really doesn't add much overhead. Block remote, and it also doesn't stop your information disclosure bug issue. So block remote images. This one, so it's basically if a module during an attack, if we are trying to load a module during exploitation across a UNC file path, then this should prevent that from being possible. Sometimes you hear of something called the, what's it called? There's a term I'm looking for. It's like not the default directory, but of the current like working folder. Like there's this term that's used sometimes when you look at MSDN, for example, if you look at the DLL safe order loading list, it's like the current directory. Well, what is the current directory? Sometimes the current directory is actually across a UNC file path, and this will block that from being possible where you're trying to load something across that connection. Validate heap integrity. So on the heap, the problem on the heap is that it's dynamic memory. It's not like the stack. The stack-based memory, it's used for finite operations. So we call a function, we build a stack frame, we tear it down, it's done. It's all done dynamically, compile inserted code based on the calling convention. On the heap, though, that's dynamic memory. It's not finite. It could live on for a very long time. Like if you leave Chrome on for a long time because you want to eat up all your memory, and you have a PDF document open in one of your Chrome windows, and you leave that window open for days, that memory just sits there in use the whole time. And so if there is some kind of a heap corruption vulnerability where we can do a heap overflow, there's it's more difficult to do checks from a security perspective on dynamic memory allocations than it would be on the stack, because the stack is finite. It's just you get in, you get out. So when do we check things like heap cookies, for example, or canaries? When do we check those? When's a good time? Or what can we put out on the heap to protect it more? Guard pages is one example. A guard page is a page of memory, 4 kilobytes, that's read, write, execute, disable. And if you go to access that page of memory, then you're going to cause an exception. Chunk and use validation, which tries to target things like use after free, where if, I don't want to go down a rabbit hole, but in C++, there's something called smart pointers that you can use that does dynamic object tracking and reference tracking. And if something's marked to be freed, can we check the environment to see if anything is referencing that? Now that's getting more into a control I'm going to talk about in a little bit called memgc, but still just different examples of heap memory validations that we can do. Arbitrary Code Guard. So this used to be called memprotect on the Enhanced Mitigation Experience Toolkit. But we typically, as an attacker, if it's a stack overflow, we like to put our shellcode on the stack. And if dep is on, we can write a ROP chain, return-oriented programming chain, pretty easily to change the permissions in memory to disable dep. That's not hard to do, unless there's a bunch of mitigations on stopping me. So if I can change permissions in memory, I can return to the shellcode on the stack where I've changed permissions and we can get execution. What this control does is says, when you're calling a critical function like virtual protect or virtual alloc, check the destination address where we want to change permissions and make sure it's not on the thread stack. Well, how does it know where the thread stack is? It looks in the thread information block at the appropriate offsets that shows you the stack high and stack low limits. So again, from a high level, it's just a little validation that says if you want to change permissions in memory, it's not allowed to be on the stack. Validate API invocation. So like it says, the intended way to call a function is by using the call instruction. It's not normal to return to the start of a function. So with return-oriented programming, we're trying to use the ret instruction to return to code sequences to accomplish some small piece of an overall goal. We string together these code sequences and we rely heavily on the return instruction. What this says is if we are going to a function entry point, validate that we are reaching it through a proper channel, like a call instruction. Simulate execution flow. So this only protects 32-bit processes, and that's the case with some of these mitigations. You'll see that some mitigations get deprecated as well, like heap spray protection, because with high entropy ASLR, and by that I mean on 64-bit OSs and 64-bit processes, it's just spraying the heap kind of loses value because there's so much virtual memory available that in order to be able to take up enough memory to make it a usable technique, it's just unlikely. No one has enough RAM on their system to be able to realistically do that. Possible, yes, unlikely though. So simulate execution flow. This says when a critical function is going to be called or about to be called, simulate or mimic the execution of the next set of instructions and look for a proper return instruction. I remember this one used to cause problems, like when a new version of Firefox would come out and I'd have emmet running, it would break Firefox because for whatever reason, when it was calling certain functions, it would mimic or simulate the execution flow, and it wasn't able to find a return instruction, and it would throw an exception and terminate. So I don't see this one as being too effective. Validate stack integrity. This is one of the first mitigations Microsoft implemented that targeted return-oriented programming. There's a technique that we love to use called stack pivoting. And the reason we like stack pivoting is because the stack pointer itself, RSP or ESP, has 3 associated very powerful instructions: push, pop, and ret. They're powerful because the ret instruction says whatever the stack pointer is pointing to, redirect execution flow to that address. So the program counter or instruction pointer is going to go to that address. So extremely powerful. Push, we can push things onto the stack or into memory, wherever the stack pointer is pointing. And pop, we can pop whatever the stack pointer is pointing to off the stack into a designated register. So very powerful instructions only associated with the stack pointer. So sometimes though, our exploit, our vulnerability that we're dealing with is out on the heap, and the stack pointer is supposed to point to the stack in memory. But if we can pivot it by exchanging one register with another, like exchange the accumulator register with the stack pointer, then we can swap those. And now the stack pointer points out onto the heap, and we can take advantage of those push, pop, and ret instructions in a different segment in memory. So what this control does is it says before we call a critical function, validate that the stack pointer is pointing where it should be on the thread stack. If it's not, throw an exception. And again, this came out in Windows 8. It was one of Microsoft's early attempts at mitigating return-oriented programming. And it was pretty easy to get around because you could pivot the stack pointer back and you could run a little loop and write your ROP chain. It was pretty, I don't see this one as a very effective control, but when combined together with some others, like the mem protection one we just talked about, it's pretty effective. Again, it's not about any one of these being the one you turn on. There's no magic mitigation. Also, it depends on the bug class as to whether or not a mitigation affects an exploit. Like that's one of the things I would do is write and weaponize a use after free or type confusion bug against Internet Explorer, and then turn on Emmet. I'd go in one at a time. I turn on the mitigations to see, does my exploit still work with this mitigation on? How about this one? How about this one? And then if it breaks it, then you focus on how to get around that one mitigation, and you hope that your target isn't using the mitigations that could stop you. So again, from a defensive perspective, it's important to understand how each one of these mitigations is associated with certain bug classes or techniques, so you know whether or not it's something you should turn on. So Code Integrity Guard, formerly Attack Surface Reduction. So we can block dangerous modules, things like VB scripting, active scripting, things that can increase the attack surface or allow us to do different types of code execution. So in here, we can specify the different modules and also offer zone exceptions that we don't want to allow. And with Code Integrity Guard specifically, we can say, I only want to allow Microsoft signed images. And we can also extend that to things signed in the Microsoft Store. But this one starts to limit, like when you're dealing with third-party applications that have a lot of requirements, these types of mitigations can actually break them. So you would certainly want to test before turning this one on. Block untrusted fonts. This one really targets bugs related to font parsing and such. For example, you all remember Dooku. And Dooku was a font parsing bug. It was a kernel code execution. Dealing with fonts is quite complex code. And so with Dooku, I believe it was a drop file. It was a Microsoft Word document, and there was a embedded font. You've probably seen it before where you open up a Word document and it says this font is unknown or not supported. Windows has a fonts folder on it. So I think it's in System32 or syswow64. And this mitigation says only fonts that are in the Windows fonts folder are permitted. If some document wants to load a font that's not in that folder, don't allow it. Because again, font parsing bugs are a thing, and that's the Dooku campaign. It was that kicked the whole thing off. So I don't think, you're probably an organization where it's okay if you turn that mitigation on. Maybe some certain fonts won't be supported, but it'll default to another, you'll be fine. So validate handle usage. This one says if you read the first bullet, the validate handle usage control checks handle references to ensure they're valid. So the example here says if a new process is created and it needs to inherit a handle to a file descriptor, something that was created elsewhere needs to be passed as a handle to something else. It records the address when the handle is created in the first place, and it gets validated before it gets passed, and to make sure that it's still accurate, it hasn't been modified. Disable extension points. So like it says here, it disables some ways in which applications can be extended or hooked over the years. You've probably seen it before, maybe not. I remember the first time I saw it was with a screen recording software. So I was using this screen recording software so that I could record my screen when I'm doing demonstrations and things like that. And when I was debugging unassociated, like completely separate processes, I would see that there was this DLL, and the DLL name was named that screen recording software. No matter what userland process is running, it was getting this DLL into every single process. And I was like, that's kind of scary. It was using this appinit DLL's registry key where it says, load this DLL in every single process. And that was when, during installation time of that screen recording software, it I gave permission, unbeknownst to me, I clicked OK when it said, do you want to allow this thing to install? It did that. So like, that's an interesting way that attackers have been able to get persistence, where they can always get a malicious DLL loaded into all your different processes. This mitigation prevents that from working. So could that break something? Yes. If you've got a process where this DLL always needs to be inserted or loaded, this would break that. So a lot of this, again, going back, you have to really understand the applications you're using and how they work. I've seen a lot of these mitigations cause problems with proprietary applications that are in-house. So they just turn it off. They're scared to use it. So they turn off for everything. But the great thing about this is it's very granular. You can go in and you can specify which processes will get what mitigations. You have that granular level of control, and you can turn on audit only. You can say this particular application never gets mitigations turned on. You have to spend the time and put in the work. But again, you will really make someone like my life more difficult by turning these things on. Disable Win32k system calls. So there's the Win32k syscall table, then there's a standard NT syscall table. If and most threads do not need to be GUI threads, if you turn this mitigation on, you greatly reduce the attack surface, because the Win32k syscall table, which has over 1,000 functions available going into ring 0 from ring 3, becomes disabled, inaccessible. So as long as that's not the case, you don't need the thread to be a GUI thread, shouldn't be a problem. So do not allow child processes. So this is if a parent process, it's called the calc killer is what some people call it, because a lot of times for demonstration purposes, an attacker would get shellcode execution and pop a calculator by creating a new process. So if a process doesn't ever need to create a child process, then you can turn this on for that particular process. If it does need to be able to spawn child processes, then you can. Valid image dependency. So this is going to help prevent things like DLL sideloading attacks. And as we know, a lot of times applications come with requirements or dependencies on third-party applications. So this says only allow DLLs to be loaded that have been signed by Microsoft. So it works great for Microsoft programs, but as you can imagine, it'll cause problems for third-party apps. Block low integrity images. So here you got an example of Chrome on the very bottom. And it says, okay, I've got an integrity level of low, medium, and untrusted. So many browsers, most of them now do sandboxing. So in the actual browser window you're interacting with is in a sandbox environment with a very low or untrusted integrity level, which means that you're running in a little contained environment where you won't be able to load things into the process space that have been downloaded from the internet. So it prevents attackers from being able to get things when you're browsing the net, preventing things like file mappings into the process space. It works alongside of user account, or not user account control, but mandatory integrity control, where it's a partial enforcement of a data flow model. Core isolation. This is the easiest one to explain is a credential guard. And I've got a little diagram on the next slide I can show you, but so this is obviously where Microsoft and other operating system vendors are going, where the goal would be everything runs in its own virtual machine, every process in its own virtual machine with a secure kernel implementation. And it really mitigates a lot of problems. And if you exploit something, you are stuck in that contained environment, and your only option to get out is to go through some broker. And that's your only vulnerability point, would be the broker. And so Credential Guard utilizes Hyper-V and implements a secure kernel instance. And this image here is a good representation of that. Typically, we only have what's on the right, where you've got one user and kernel land space, ring 0, ring 3, and that's it. And so all the drivers and things like that are in kernel land. You've got something called the hardware abstraction layer that talks directly to the hardware. And tools like Mimikatz can exploit or inject into the LSAS process and steal the credentials out. And it works great. We've all used that before if you work in the attack space. So with Credential Guard, it utilizes Hyper-V. So now you've got this hypervisor shimmed in between the kernel and the hardware. So there's two kernels running now, as you can see, side by side. And then you've got this isolated user mode process. Inside of there is LSAISO. That's LSAS, but in the kind of quarantine environment. And that's encrypted, and that's where the real credentials are stored. So if you use Mimikatz, you're over there in userland in VTL1, and you go and you try to inject in LSASS, you're not going to get anything because LSASS is over somewhere else in a different kernel implementation. It's very interesting because you can't even, with a kernel debugging session in VTL1, you can't even get over to the secure kernel implementation. So as you can imagine, if we put everything into an isolated user mode process in different secure kernel instances, that's really going to mitigate a lot of problems. So I would definitely see that coming at some point in the future. All right, so quick demo. I know I'm almost out of time here, so I'm going to make this really fast. This right here, I just choose this one because it always brings back bad memories. Corland coder, Peter van Nickhout, good friend of mine in Belgium, probably heard of him, brilliant individual, very generous. He and I were not together, but separately, writing a lot of use after free exploits against Internet Explorer. And you could make $10,000, $20,000 at the time by selling to an ethical buyer who would disclose it to the affected vendor and get it patched. You could make a lot more money going unethical route, but that's not what we're talking about. And so in 2014, Microsoft introduced a couple new controls. One was isolated heap, and another one was memgc. And I just wanted to show you the code here real quick. So this is code written by Keen Team, and it's a use after free vulnerability that normally wouldn't be exploitable. You wouldn't be able to get what you want to get out of it because of the mitigations. Microsoft started in isolation, in a separate heap, in a separate area of dynamic memory. They started to put HTML objects like div, span, table, button, all those HTML objects, so that when a use after free vulnerability would be triggered and the attacker would go to replace the freed allocation, they can't, or not easily, because the allocation that's been freed is somewhere else in memory. And when the attacker does their allocation, it goes in the default process heap. So it's kind of segmentation. They also implemented this check called memgc and deferred free that said if an object is marked to be freed, before we give that object back to the heap manager for reallocation, validate that no one needs it. And it really did a great job mitigating a large number of use after free bugs. Well, what Keen Team did is they discovered that there's a threshold that they get around right here. It says, allocate 100,000 bytes and then free it, and you get around the deferred free protection, at least initially. And then down here, they did something neat. And they said, well, since the isolated object is unreachable through normal allocation means, like if we're allocating a JavaScript string, then put it in isolation. Well, since that's the case, we can groom the heap a bit, and we can do an implementation where our object does end up replacing the freed object out on the heap. So very neat. I can't go into any more technical detail, although I'd love to because we're in a tight time crunch here. But if we run this, it's just showing you that it works. So when we allow the code to execute inside the debugger, I know it's not that exciting, but you can see the accumulator register holds 42424242. And that's because those mitigations, isolated heap and deferred free, were circumvented. And we were still able to get control of the registers in this case. So it's just going to show you that any one mitigation is not enough to solve all the problems. And sometimes you need many mitigations. And so my last thing, the takeaway I'll say before I stop is take the time to understand what each of these mitigations are doing, understand how much one mitigation affects a particular attack technique or a bug class, and choose which ones make the most sense. Yes, you do have to do validation and test them, but think about your goal. Your goal is to work together, offense and defense, to use the mitigations that are going to stop attackers from being able to exploit things. And these do a fantastic job, and sadly, they're hardly being used by anyone. So with that, I will stop. I know we're at time, but I'll hand over to George and such.
You did fantastic. Your channel here is popping like you have no idea. It's going to take you like an hour to read through it. One excellent presentation, as always, very technical. Lots of people learning new stuff and some questions around that. So let me jump into some questions. I think some of these you answered. When you were talking about ASLR and that not all modules are compiled like that. How does it work? Like if someone didn't compile using ASLR and the operating system has the ability to enable it, how does that work? If, let's say, a program didn't leverage that technology, can it still be enabled?
Yes, so normally when you compile a module, the compiler will choose an address, a virtual memory address where it always wants to be loaded. And sometimes that address where it wants to be loaded is already taken, so we have to fix it up or relocate it, and it all works fine. If someone goes through the effort, or it's an old module that was not compiled with dynamic base flag in Visual Studio, for example, and we turn on mandatory ASLR, it'll just patch it, and it will record where it's been moved to, and it should just work. The only time it's going to break something is if for some reason, if a process has a hard dependency on something being at a specific address. Otherwise, it'll work fine.
And that's where you said that teams have to work together to turn these on one by one to make sure that nothing breaks on these older programs that might not have been compiled. Fantastic. What about core isolation, right? I think a lot of people made the immediate click that, oh, that's what Credential Guard uses. And now more and more are coming. Now, you've been doing this for a while, and we've talked about this in the VMware space, right? The whole cloud burst or breaking out. Do you see the ability maybe in the future of being able to kind of break out of that core isolation? Would that even be a thing?
Yeah, I mean, it's the thing you're doing is greatly reducing the attack surface again. And so if you assign Tavis Ormandy to it, yeah, he's going to break it, right? I mean, but it just greatly reduces the attack surface to where if you're stuck, like let's say you're in a prison and there's only one door. I mean, your only way out, if you can't dig, everything's, you're in a steel box basically, and there's one door, that is your broker, that's your way out. And you're going to focus all your time on trying to find vulnerabilities in that area. And once that gets picked, once there's nothing left, there will always be something, but it's going to get harder and harder. I mean, I think I remember the XKCD comic that said something like his system's encrypted with some crazy encryption and we can't get in. It's like, someone get the $5 wrench, and hit him over the head till he gives it to us. Maybe we'll go back to physical attacks. I don't know.
That's hilarious. Awesome. Well, thank you so much.